Okay, welcome back. What did we learn in the last class? We had introduced BJT in the last class, right? And also the different kinds of transistor and the applications of transistors. There are a wide variety of applications of transistors. We had discussed about that, and we said that we will start with BJT because the BJT is the simplest. Starting from PN junction, it's actually two PN junctions back to back. We just started BJT and the concept of BJT, so today we will start in full flow about BJT. There are many things to learn about BJT, how it operates, what is the gain, how does it amplifies the signal, what are the various aspects of design that one should be aware of when you try to make a BJT and so on. The first thing we learn is the working of a BJT. Okay, and a BJT has several components of current. We have to carefully identify the different components of current, okay, and eventually we will try to understand what are the different parameters in the device that have to be optimized to get the best performance. Okay. So, first thing first, we will start with the band diagram of BJT where we stopped last time. We will come to the whiteboard now. Okay. So, what did we tell in the last class? I told you that a BJT is a transistor. It has two back to back PN junction diodes. So, I have an NP and then I have a PN. I told you this is called emitter, this is called base, and this is called collector. So, collector is typically the output where you collect the current. Okay. And current between the current that is coming out at the collector is actually dependent on the input at the base. So, that is how you control the current. If you recall, between point A and point B, the current that comes is controlled by third point C. So, that is why transistors look like the third point C here is the base. So, the base will control how much current comes out to the collector. That is how a transistor action will be achieved. Okay. So, I told you that if I have a PNP junction like that, the whole idea is that the current coming out of the collector, I will call it IC, is controlled not by the voltage at Vc here, but not by the voltage here, but by the voltage or the current that you are applying at the base. So, the output voltage Vc should not have an effect on the current IC. That is what the transistor is about. Okay. So, if you draw the equilibrium band diagram, then the Fermi level has to be same everywhere, and N type, this is a PN junction, the first one is a PN junction. So, it looks like this, right. It looks like this, and then next is an NP junction. So, again it will look like this, right, look like this. So, I can assign that doping, there are different dopings here, there is a P type doping here, there is an N type doping here. So, I told you that this is the base emitter junction, this is the base collector junction, and its equilibrium, there is no current flowing. Okay. The way you operate a BJT, the most common way to operate a BJT so that you can get gain and other things is that your emitter and base, this junction is forward biased. So, you will apply, this is N, this is P, this is N. So, you remember that this is a hole doping. Okay. This is N. So, you forward bias this emitter base junction, it is a PN junction that you are forward biasing. So, put negative here, positive here. Okay. You are forward biasing this junction. So, the moment you forward bias this junction, the depletion width will shrink, will become very narrow, and the barrier height also will reduce. So, you will have something like that. Okay. So, this is the hole Fermi level, quasi Fermi level, this is the electron quasi Fermi level. There is a difference here, the difference is the applied voltage Q VBE, this is called the applied voltage you are doing here, VBE. Okay. And you are injecting electrons from the emitter to the base, because this is N type, this is P type, and you are injecting holes from the P type from the base to the emitter. That is how a PN junction works, that we have learned. Okay. Now, this junction is reverse biased. So, you will put, essentially what you will do is that you will put a positive bias here and negative bias here, sort of. Okay. Now, you might think that I am putting a negative bias here, I am putting a positive bias here, what is this going on in base? Am I putting a positive bias or a negative bias, right? Essentially, whatever voltage you are applying to the base, you apply a more higher voltage at N type, that is, that makes N type more positively biased than P type, and this junction, you are going to so that this becomes reverse bias junction, that becomes reverse bias, this becomes reverse bias, okay, and this becomes forward bias. Okay. This becomes forward bias and this becomes reverse bias. You want the base collector to be reverse bias, so you apply a more higher positive bias here, actually, that you can say. In reality, of course, there are different modes of operation. We will come to that. Okay. Like common base, common emitter, there are different modes of operation in which you can ensure that this junction is reverse biased and the base emitter junction is forward biased. Okay. I will just remove the bias right now so that there is no confusion. So, this junction is reverse biased. The moment it is reverse bias, what will happen? Remember how a reverse bias junction looks like? A reverse bias junction has a very large depletion length width and a large barrier height like this. This is collector, this is base. So, the depletion is very large, the field is also very large. So, these electrons that are injected from the emitter to the base and the holes are injected from the base to the emitter. So, this will come out through the emitter, it will contribute to some emitter current. Okay. Now, these electrons that are injected, I am telling you how a BJT will work. The electrons that are injected, these electrons will now diffuse across base, some of them will recombine because base is p type dope, right. The base is p type dope, which means holes are majority. If holes are majority, then when you inject electron from emitter, these electrons that you are injecting from emitter, they will recombine in the base. Some of them will recombine in the base, some of them will not recombine. Whichever electrons have not recombined will reach this edge. This is the depletion edge. This is the depletion edge. As soon as they reach the depletion edge, this reverse bias, the huge field is there, will immediately sweep away the electrons to this side. These electrons are coming from the emitter, by the way. Some of them have recombined in the base, some of them have not recombined. The ones that have not recombined are swept away to the other side, they contribute to the collector current. So, to have a higher collector current or output current, what are the things? One thing is that I want more electrons to be injected from here, and secondly I want very few electrons to recombine here, so that most of the electrons reach the collector and most of them come out here. You agree? Most of them come out here, right. I don't, if most of the electrons recombine and die in the base, then at this edge if very few electrons reach, then the electrons that are coming out here will be very few and the collector current will be low, the output current will be low. You want generally the output current to be high in many applications. Okay. Okay. So, you want that there should be as low recombination as possible in the base, as low recombination in base as possible. Okay, as possible. You want electrons that are injected from emitter should recombine negligibly in the base, otherwise you will not get current in the collector. Okay, that is one thing. Now, there are different current components here actually, we should take into account very carefully. Okay. So, what I will do is that I will draw the schematic here and I will also draw the band diagram, so that we know this is emitter base, this is collector. Because the emitter base junction is forward biased, okay, because the emitter base junction is forward biased, this is collector, because the emitter base junction is forward biased, what will happen is that you will have very little depletion here. The forward bias junction has very little depletion, you can almost, this is a very small depletion, and the base collector is reverse bias. So, the base collector depletion is large, the base collector depletion is large. Okay. Now, you see, you have the band diagram that looks like this, the band diagram that looks like this. Okay. This is the emitter, this is the base, this is the collector. So, what are the current components? See, one component is that electrons are injected from here to there, that contributes a current from the emitter, I call it IEN. So, the electrons are actually injected from here, so IEN will come out this side. Forget the direction of the current now, you just concentrate on the current, the magnitude. Okay. The direction can be thought of later. This is the electron current, that is because emitter is injecting electron because of this junction is forward biased. This junction is forward biased, right. This junction is forward biased, that is why electrons are injected, otherwise they would not be injected. So, electrons are injected from emitter, this is n type, this is p type, this is n type again. So, electrons are emitted from the emitter to the base. So, that constitutes the electron current of the emitter. The idea is that most of the electrons should reach this edge, so that they are immediately swept away this side. Whichever electrons have reached this edge will be swept away, and I call that collector current because of electrons that are coming from the emitter, I and C. The collector current that is coming because of the electrons from the emitter are coming here, diffusing across the base and going here and getting collected in the output, that is as the output current. Okay. While because this is forward bias, this is p type dope, no. So, lot of holes will be there which also will be injected across this, right. Holes will be injected across this, the current direction also will be in this direction, this current also is actually in this direction, but that is okay, not a problem. Let us not focus on the direction now. So, holes are injected this way, I call that IEP because that is also an emitter current. Electrons going this side, holes coming this side, they are both emitter current, one is the electron component, one is the hole component. So, the total emitter current is actually the injected electron, this one, plus the back injected hole, which is this one, both are in the same direction, which is this. Okay. So, that is the total emitter current. Now, the some of the electrons that are going here will recombine in the base and decay. You remember, whenever you are injecting electron to the p type base, this is x, then the excess electrons will decay. So, some electrons will decay here, and that decay is in like recombine with holes, and because they will recombine with holes, that will give rise to a base current. So, here I told you that there will be an emitter current IEN, forget the direction, there will be also a injection of holes. So, the IEP, they are both in same direction by the way. Because there will be some recombination down in the base, there will be a base recombination current, and to supply that holes that are recombining in this region, electrons and holes are recombining to some extent, no. So, to maintain that balance of the holes, you have to inject holes from the base contact. Okay. So, that is a base contact that will inject holes. I call that IB recombination. You are supplying some base current here, because the electrons that are injected here are getting recombined within the base, some of them. So, you want to, that is a component which is the base recombination current, that will be responsible for electron hole recombination here, and then the electrons which reach here will be swept away immediately. So, that is INC, I told you, that is the electron current at the collector that has come out, because from the emitter side that has come out, and this is the current which is of most importance to us, because that will contribute to gain, amplification, output power, everything. Okay. Now, because this base collector junction is reverse bias, there will be a reverse leakage across this junction. There will be a reverse leakage across this junction. That reverse leakage will be, I can say I base collector, that will any minority carrier that comes here is swept away that side, any minority hole that is here comes here will be swept away that side. So, the direction of current is in this direction, both of ways. That is a base collector leakage current that comes. You remember, in a reverse bias junction, J equal to minus J naught, ideal diode, even they can be recombination also, generation recombination. So, this is the reverse saturation current, this is the reverse saturation current that will be there, I call it IBC comma reverse. So, this is the reverse saturation current that is there across the base collector junction, one component because of electrons, one component because of holes. You can actually do it in two way. One is that IB, this is the electron leakage current, and this is the hole leakage current, both of them together you add up, you get the total base collector reverse bias current. This is basically nothing but J naught, if you remember, which is Q Ni square dP by LP into 1 by Nd, all those things you remember, that is actually this current. Okay. So, that is a reverse leakage current there. In a good BJT, of course, or in a good PN junction, you want the reverse leakage current to be low, because if the reverse leakage current is high, then you defeat the device, there is no point of the device. So, typically the reverse leakage that is happening across the base collector junction will be very low, say picoamps or femtoamps, whereas this current will be in the range of milliamps or so. So, typically this base collector reverse current that is there can be neglected. Okay. We can neglect that most of the time. So, the base collector reverse current that is there here, we can, that leakage current can be neglected. So, what are the main currents now? We have discussed many currents, right. So, let us draw the band diagram again under operation. So, base emitter is forward bias and the base collector is reverse biased. Okay. So, electrons are injected from here, some of them recombine, they fall here, and as soon as they go to the edge, they immediately swept away here. Okay. So, I told you there is a base collector reverse bias here, BC reverse, which we typically ignore. So, the main components are electrons are injected from emitter to the base. So, that constitutes IEN. So, you are injecting electron from the emitter to the base. Base also injects holes, this is a p type. So, it injects back here. So, that is IEP. So, that is another component IEP. This component is emitter current, but we can also include that as a base current also, because it is coming from the base. So, either way this component can be taken, this is, you can say, emitter current. The base current is the current that is recombining here, IB recombination. So, there is some current that is recombining, because the electrons are going here, they are decaying, anytime they decay there will be recombination current. So, this is the base current. Sometimes, as I told you, you can also include this as this both as the base current, and finally, the electrons that reach here are swept away. So, that is your collector current. Now, what are the things that you should look out for? We want the output current is the collector current, output current is the collector current, which is INC. You want maximum number of electrons that are injected from here to reach the collector. I want maximum number of injected electrons, I want maximum number of injected electron from emitter okay, to reach the collector. I want them to reach the collector, because if electrons emitted from the emitter do not reach the collector mostly, then it means they are all dying out here. It becomes a 2 terminal device, it is not a 3 terminal device. To increase the output current and hence the gain and many other things, you want most of the, almost all the electrons from the emitter that are injected should go and reach the collector, and this back injected holes that are there, these holes also contribute. There is a large current and this will come out from the emitter contact here. If you make a contact, this will come out. This IEP, this back injected whatever holes are coming out now, these are actually, when I say back injected, this is basically a PN junction. The P will inject holes this side, no, you remember that from PN junction, yes. So this component actually does not contribute, this does not contribute to output current, to INC. INC is the output current. So this does not contribute to output current. So this is a useless component, this is a bad component, this is a bad component of the current. Why? Because this component comes out through the emitter here, this does not contribute to the collector current. So I want that in the emitter current, this is the total emitter current, no, I want this component to be as small as possible compared to this component. So I want most of the current to be because of, I want most of the emitter current to be because of electron current here, right. That is the first condition I want, otherwise this is waste, this is not coming out through the collector. And also I want that collector current should be, you know, I want the collector current has, some of them has recombined here, some of them are reached, whatever has reached is contributing to this current, no, the collector current. So I want that this ratio, the collector current that I am getting here divided by this emitter current that I am putting, not the total emitter current, but the emitter current because of electron, this electron emitter current, this should be as close to 1 as possible. Matlab 100% of the electrons that I am emitting here should be able to reach here, that is the idea. Because if this reach 90% of them reach here, matlab 10% has decayed here, okay. So that reduces your efficiency and your gain. So you want that maximum number of electrons from the emitter should reach the collector. So the collector current because of electron divided by the emitter current because of electron, this ratio should be as close to 1 as possible, okay. So that is a very important thing. So there are some terms that people define, okay, there are some terms that people define. We can also define those terms because those are very important in understanding the transistor. So I will again draw the band diagram here. So this is base emitter forward bias, this is base collector reverse bias, okay. Electrons that are injected here, some of them recombine, some of them reach here, maximum reach here. Once they reach here, they are swept away here and collected here. The holes also injected, back injected, which is a useless current component IEP. This component is IEN, and the collector current here you get is INC, okay. So there are few things we define. One is called base transport factor, one is called the base transport factor, one is called emitter injection efficiency, emitter injection efficiency. These are some of the terms we will define, okay. One of them is called current transfer ratio, current transfer ratio, and one of them is called gain, okay. These are the 4 things that we should be generally aware of, because these 4 things will define how well your transistor will behave, okay. These 4 things will. So what are these things? So base transport factor is called capital B, emitter injection efficiency is called gamma E, current transfer ratio is called alpha, and gain is called beta, okay. These are important terms. So remember, electrons are injected from emitter, some of them recombine, most of them reach here, whatever has reached here will be swept away to the collector. They are the collector and the output current is constituted by electrons from the emitter. So we call them collector current because of emitter electron current. This is the IEN that is injecting, I mean the direction will be this side, electrons that are moving here and are going there. There will be some base recombination current here because electrons will decay in this as they move. There is a base will also inject, back inject holes here, which is IEP, that is useless. And of course there is a base collector reverse bias here, reverse current, which is very low, and I am neglecting that, okay. We are sort of neglecting that. So first I will discuss what is base transport factor B. The base transport factor B is defined as the ratio of the collector current, this one, divided by the emitter electron current, this one. If you look carefully into this, it is basically what fraction of these emitter electrons have reached this point and gotten collected as a collector current. So, this is the ratio of the collector current because of electrons that have come from emitter, which is dominant current. There is no other collector current. This leakage is very, very low. Okay. So, this is an important factor, and the base transport factor should be as close to 1 as possible. That means most of the electrons that are injected from emitter should have reached the collector. Okay. That is the base transport factor. The emitter injection efficiency gamma E, which is this, is defined as the out of the total component of the emitter current IEN plus IEP. Okay, this is also emitter current, this is also emitter current. Out of these two component, what is the fraction that is useful, which is IEN, because this is the useful current that will go and come out as collector. This is a useless factor that will come out from the emitter only. Okay. So, what is this fraction? How well is the emitter injecting electron? If this ratio is close to 1, it means most of the current in the emitter are because of the electrons, not because of the hole. If this is half, it means there is equal number of electron, equal number of hole. That is a terrible device. You want this number to be as close as 1 as possible, like 0.99 or so. Okay. Then the third factor is current transfer ratio alpha, which is defined as the collector current to the emitter current. Okay, it is defined as the collector current to the emitter current. And what I can do is that I can define this as the collector current is mostly your collector current is because of the electron that have come here. This base collector component that contributes to collector current is negligible, I keep telling you. So, I can write this as the collector current because of emitter divided by IEN into IEN by IE. I can write that the same thing. Now, this quantity, this quantity, this is this actually, because this I is the total current, this is the current, right. So, this I can write as gamma E, and this quantity is actually beta B, not beta B. So, I can say that your current transfer ratio alpha is base transport factor B times the emitter injection efficiency E. This should be also as close to 1 as possible, because this should be as close to 1, this should be as close to 1. Okay. That is the thing. Okay. And finally, I have gain. Gain is defined as the output current, which is the collector current, okay, divided by the base current, divided by the base current. Now, the base current technically has two components, one is the back injected emitter, okay, and one is a recombination current, okay, one is the recombination current. But if you put the various expressions that we have learned till now, okay, this will come out to be alpha, this is beta by the way, 1 minus alpha, this is called beta. Okay, this will come out to be alpha 1 minus alpha. So, for example, if the current transfer ratio is 0.99, that is the current transfer ratio which is defined as total collector current by the total emitter current. If this is ratio is 0.99, it means out of the total emitter current, both electrons and holes combined, okay, out of this 99% of them has reached the collector. I mean in not 99% of that, the collector current is 99 percent of the total collector current. Okay. If this alpha is 0.99, then beta will be 0.99 divided by 1 minus 0.99. This will be 0.99 divided by 0.01, which is 99. So, the gain of the device will be 99, which is the output current divided by the base current. So, a higher gain means the device has better gain basically. So, the collector current should be much larger than the base current. In other words, the base current should be very small, and the base current can be small when this back injected component is small and when the recombination is small. Please remember that if most of the electrons recombine in the base, then the number of electrons reaching the collector will be very low, your beta will be low, your gain will be low, and you will have a very bad device. Okay, you want the maximum electrons to reach and go. Okay. So, these are different terminologies that are used in the transistor in the BJT parlance. Okay. Now, if you again look at the band diagram, I will draw the structure again. So, this is suppose your let me draw a bigger structure so that I can correlate easily. So, this is your the schematic. So, suppose this is emitter N type, this is base P type, this is emitter, again this is collector. Okay. Now, because there is a depletion here, a small depletion, that is okay, there is a depletion, it is a small depletion, some part of this has gone in the depletion, some part of this has also gone in depletion. Now this has a wider depletion, a large part of that towards the base has gone into depletion. This is the depletion towards the base, and this is the depletion towards the collector. So you see, base is the most important part here, okay? You have to look carefully. This distance is actually the what has left behind of the base. What was initially the base was this, but what has left behind in the base is this. So this, what was initially the base, you know, is called the metallurgical base width, WB is called metallurgical base width. The reason is it's called metallurgical base width is because this is defined by the metallurgy, like this is defined by the junction depth. So this is the boundary of the base, this is the boundary of the base. So this is the actual the metallurgical base width, but because of depletion in a real operation, okay, only this part has remained as base, the rest part has been eaten away by the depletion, or you can say the depletion has taken that away, right? Depletion has taken that away. So this part, this shrunk is called WBN, it's called neutral base width, it's called neutral base width, okay. Neutral base width is the base width which actually matters in the device operation, because as soon as the electrons reach this edge, no, this will be swept away here. So what matters is the neutral base width only. So neutral base width is the most crucial parameter, we will come to see that. Of course the doping is also very important, so this will determine many of the things. Now from your logical insight, you know, from the intuition, you know that when I am injecting electrons from the emitter side to the collector over the base, they will recombine in the base, and there is a base recombination current, we all know that. We want the base width, this base width total, I mean neutral base width or whatever, this base width to be narrow. We want the base width to be narrow. Why? So that maximum electrons that I am putting can quickly go to this side and get diffused this side, I mean they can be swept away this side. If the base width is large, then what will happen is that most of the electrons that are injected will recombine. I want to minimize the fraction, of injected emitter current which is recombined, injected emitter electrons, okay. I want to minimize the fraction of injected emitter electrons which recombine in the base, because if most of the electrons that I am injecting recombine in this base, then the output will be very low, and most of the electrons will recombine in the base if the base is large. So the narrower the base is, suppose I have a base width like this is base versus another base that is like this, and then collector here, there is emitter here, there is emitter here, okay. So when I am injecting electron here, some of them will recombine, most of them will come here, but when I send electron here, it is such a large base that most of the electrons will recombine, there is nothing left here. So you want to shrink the size of the base, you want to make the base narrow, so that very few electrons recombine in this region, most of the electrons come to the collector. So if you keep a wide base like this, a very thick base like this, then most of the electrons that are injected will be decaying, and they will lead to very low current. So the rule, a golden rule is that the width of the base should be very narrow. Only a very narrow base will give you a higher gain or higher current transfer ratio or higher, you know, base transport factor. You want this quantity to be very short, okay. So the base should be narrow, okay. Only then you will get most of the electrons that reach the collector. You getting my point, right? This is a transistor we are talking about, by the way, okay. And this is emitter, this is base, this is collector, each of this is N, this is P, this is N. You will have different doping, this is N type doping, this is P type doping, this is N type doping, but the N type doping and emitter and collector could be different. ND is not a good way. So I will put this is ND emitter, this is ND collector, they can be different doping, and because I am giving this like this nomenclature, I will say NAB, this is base doping. Now if you remember, if you look at a PN junction, just a normal PN junction, electrons, when you forward bias the junction, which means you forward bias the junction like this, electrons are injected from here to here, holes are injected from here to here. How do you make sure that electrons injected this side results in a more dominating fraction of the current then holes coming this side. You want the holes coming this side to be minimum because that is useless, that comes here, right. So, how do you make sure that holes injected to this side is much smaller in quantity and magnitude than the electrons injected to this side? Do you remember that? See, the electron that is injected to this side will give you a current which goes as density I am talking, so area I will ignore, q dn, because the electrons are injected, no, by ln into ni square by the doping in this region which is Na here, plus this into e to the power qVa by kT minus 1, that is your, you can say that is your electron current to this side, and the whole current that comes this side is given by q dp, if you remember from your p-n junction classes, Ni square by the doping on the Nd side, this side Nd e to the power qVa by kT minus 1, this is the Va that we are applying. Okay. Most of the terms are equal here, I mean there are small differences here, you cannot differentiate except Na and Nd. You please look carefully, if you are doping on the, it goes inversely as the doping on the other side. If the doping on the p side which is Na is very low, suppose this doping is 10 to the power 15 this, and suppose the doping on this side is 10 to the power 18, then this quantity will be much larger than this quantity, right, because this is 10 to the power 18. So, this will go as q dn by ln Ni square 10 to the power 15 exponential of something. This is the current because of electrons from n side to p side, plus this is electron, this is the other component q dp by lp Ni square by 10 to the power 18 something. This is because of holes from p side to n side. You see, this is 10 to the power 15, this is 10 to the power 18. This quantity will be much smaller because there is a 10 to the power 18 in the denominator. This quantity will be much larger because there is 10 to the power 15 in the denominator. So, electron from n to p will be much larger than hole from p to n. This is the whole component of the current here, and this is the electron component of the current here, which means if I dope the n type much higher than p type, which means if I have a structure like this, n is very highly doped n plus, p is lightly doped p minus, then the electrons injected this way will be much more than the holes injected this way, and that is how I can make sure that in a BJT this back injected current component of IP, useless current component, is minimized by making sure this is doped high, and this is doped low. In that case, electrons from here to here will be much larger and holes coming from here to here will be much smaller. Okay. So, we shall end the lecture here today. We have had enough of discussion on BJT as of now. So, what did we learn? We had gone ahead with the band diagram of BJT, the basic operational principle of BJT. We have defined the emitter base collector regions, their dopings, their thicknesses, at least the base thickness. We have not come to emitter and collector thickness yet, we will come to that later. We have also defined some many very important crucial parameters like gain, current transfer ratio, base transport factor, emitter injection efficiency, and I told you that many of these, how to increase many of these parameters. We have discussed several current components in the device, primarily the current because of electrons injected from emitter to the base, the recombination that takes place in the base, and the electrons that reach the collector which contribute to collector current. The back injected holes from base to emitter useless, we want to minimize that. So, we discussed strategies to minimize that you have to dope the emitter high and dope the base low. To make sure that most of the electrons from the emitter reach the collector, your base has to be also narrow, otherwise they will recombine and die mostly. Okay. So, these are important things that we have discussed. Now, we will go and write down the current equation in the next class, derive the equation. These are very easy p-n junction equations, by the way, and the base is the most critical. Okay. When electrons are injected from emitter to the base, they are minority carrier, that is they are decaying. So, that part we will focus on the next class and we will take it from there. Okay. Thank you for your time.